Welcome to this EWRB Electrical Service Technician Training course. I'm Aria, an electrical tutor working with Roy. In this course, I'll guide you through all the topics covered in the EWRB Electrical Service Technician Exam Teaching Guidelines. Topic 8.3, Power and Energy. Welcome back. In the previous lesson, we talked about electrical circuits, how current flows in series and parallel connections, and how we measure voltage, current, and resistance safely. Today we'll move on to topic 8.3, Power and Energy. This topic is where we connect all that theory to something real, how much electrical work is being done, how efficiently it's done, and how we measure it. Let's start with the first part, understanding the relationship between voltage, current, and power. Topic A, the relationship between voltage, current, and power. Every time current flows through a circuit, electrical energy is converted into another form, like heat, light, or motion. The rate at which that energy is used is called power. We can describe it in simple words. Power equals voltage multiplied by current. Spoken as a formula, P equals V times I. This means that if either voltage or current increases, the power increases too. For example, if you have a heater that draws 5 amperes from a 230 volt supply, the power is 230 multiplied by 5, which equals 1150 watts or 1.15 kilowatts. In every circuit, whether a lamp, a motor, or a toaster, that same rule applies. Power tells us how much work is being done at that moment. Topic B, units in which power is measured. Now let's move to the second part, the units of measurement. The unit of power is the watt. 1 watt means 1 joule of energy converted every second. For practical use, we often talk in kilowatts, which are thousands of watts. So 1 kilowatt equals 1000 watts. When you read a nameplate on an appliance, such as 2 kilowatts heater, that means the appliance converts 2000 joules of energy every second when running. Power ratings help us select the correct size of wiring, circuit breakers, and fuses. If the power is high, the current is high, and the conductors must safely carry that load. Topic C, Power formulae and their use. In Topic C, we'll look at the main power formulae and how to use them. There are 3 ways to calculate electrical power depending on what information you have. First, P equals V times I, this is the most common. Second, P equals V squared divided by R, if you know voltage and resistance. Third, P equals I squared times R, if you know current and resistance. Let's say we have a 230 volt element with a resistance of 46 ohms. Using the second formula, P equals 230 squared divided by 46. That gives 1150 watts, the same as before. All 3 formulas describe the same thing, how electrical energy is converted into work. Knowing how to use them lets you check nameplate data, test results, or calculate cable ratings in practical jobs. Topic D, transposing the formula to find unknown values. Now let's move on to how to rearrange these formulas to find missing information. If we need to find voltage, we can rearrange the main power formula to V equals P divided by I. If we need to find current, we rearrange it to I equals P divided by V. And if we need to find resistance, we can use the formulas R equals V squared divided by P, or R equals P divided by I squared. For example, suppose a motor is rated at 1.5 kilowatts on a 230 volt supply. To find current, divide 1500 watts by 230 volts. That gives about 6.5 amperes. We speak that as current equals power divided by voltage. Being able to rearrange and use these formulas is part of the EST written exam, and it's also a skill you'll use daily when checking electrical loads or designing service circuits. Topic E, relationship between voltage, current, time, and energy. Next, let's talk about energy, which is the total amount of electrical work done over time. Power is the rate at which work is done. Energy is the total work done over a period. We find energy by multiplying power by time. Spoken as a formula, energy equals power multiplied by time. If a 2 kilowatt heater runs for 1 hour, it uses 2 kilowatt hours of energy. That's the same unit used on your electricity bill, kilowatt hours. If the same heater runs for 3 hours, it uses 2 times 3, which is 6 kilowatt hours. That equals 6 units of energy consumption. So remember, power tells us how fast the energy is being used, and energy tells us how much has been used in total. Topic F. Units in which energy is measured. Now let's talk about how energy is measured. The unit of energy is the joule, but in practical work we use kilowatt hours. 1 kilowatt hour means 1 kilowatt of power used for 1 hour. It's equal to 3.6 million joules of energy. Electricity meters in homes and businesses record energy in kilowatt hours. Each unit on the power bill represents 1 kilowatt hour of energy used. Understanding this helps when you estimate running costs or when you explain energy efficiency to customers. For example, a 1000 watt heater running for 1 hour uses 1 kilowatt hour, but a 500 watt heater running for the same time only uses half a unit of electricity. Topic G. Converting horsepower to watts and vice versa. Finally, let's look at the relationship between horsepower and watts. Horsepower is an older unit used mainly for motors and engines. 1 horsepower equals approximately 746 watts. So, if a motor is rated at 2 horsepower, that's 2 times 746, which equals about 1,492 watts, or roughly 1.5 kilowatts. To convert the other way, divide the power in watts by 746 to find horsepower. For example, a 3000 watt motor is 3000 divided by 746, which equals about 4 horsepower. Understanding both units is useful because you may still see horsepower used on older motors, compressors, or service manuals, even though modern equipment lists kilowatts instead. Bringing it all together. Let's now bring everything together to finish topic 8.3, Power and Energy. We began by understanding how voltage and current combine to create power, the rate at which electrical work is done. We then looked at the 3 power formulas and learned how to rearrange them to find unknown values. We saw how power over time becomes energy, measured in kilowatt hours, and how that relates to your energy bill. Finally, we learned how to convert between horsepower and watts for motors and other mechanical loads. Summary. To summarize, power equals voltage times current, energy equals power times time. Power is measured in watts, and energy is measured in kilowatt hours. 1 horsepower equals 746 watts. These relationships are the foundation for testing, load calculations, and appliance efficiency, all essential skills for an electrical service technician. That concludes topic 8.3, Power and Energy. In our next session, we'll move on to topic 8.4, Electrical Conductors, where we'll learn about conductor materials, their properties, and how to select the right type for different electrical applications.